Okay, so yes, it's recollection of old time. So I met, maybe not personally, but I saw Vershik for the first time on Rochny's seminar on ergodic theory, so it was 1960. So it was a long time ago. And most of what I can say is of this time. And Rochny was very enthusiastic about Vershik participating then, and Vershik was doing something else. I think he was close to computer science, what was not computer science exactly at that time, but linear programming and convexity and things like that. And Rochny was, in my presence, convincing Vershik to switch to ergodic theory. And on the same time, kind of explaining to other people in my presence, I was a student, that how he was highly valued philosophical way of thinking by Vershik. And indeed, Vershik had a really strong influence around exactly by generating ideas of kind of philosophical type, conceptual kind of thinking. This was his characteristic feature all along. And so specifically, what I remember of that time, it's 3 or 4 topics he was bringing forth, and one of them was combinatorics of particular polyhedra, which was motivated, I believe, by the kind of the simplest case of the polyhedra of bistochastic matrices. So we have matrices where you prescribe which it is entries, kind of entries of a matrix, and you prescribe they're positive matrices, so they're positive, and you intersect them with a plane which is defined by hyperplane, and this hyperplane, the faces of your polyhedron, beside those which define as positivity, the faces are corresponds to defined by sums of column and rows to be one. So in general terms, you have a space, Euclidean space of matrices, and their permutation group X. Actually, there are 2 permutation group Xing. It's product of 2 permutation group and actually involution between them. So it's kind of a word product, not word. I'm sorry, it is a different kind of product, and all faces are lying on the same orbit. And so what's remarkable, this is a theorem of, I don't know, many names. It may be associated with Birchhoff, Neumann, who knows. But the property here that vertices also lie on the same orbit, right? And this is a very exceptional phenomenon. When you have a group acting on a space, you take convex hull, and you want to have a polyhedron where both faces and vertices are on the same orbit. And this is certainly highly exceptional. It almost never happens. But then you may still ask what happens when either vertices or faces, which is the same by duality, either of them on the same orbit, and what happens to other faces. And among them, there are indistinct polyhedra. When you have of 2 permutation group operating this way, you have several of them. So you have an n-dimensional array. So in a very high dimensional space, n-dimensional array, like cube, part of a cubical region in a lattice, and you prescribe this. You take this. Then, of course, on there your permutation group X transitively on faces of given dimension, and you say the sum of entries along these faces are given to you, X equals 1. And you have positive arrays of this nature. What are other faces there? And the number of them will be, of course, very large. It will be factorially large, more than exponential. But what I'm using about them, of course, they're all rational. And the question, what is the arithmetic of those? And there were some students around him solving that in special cases, but the problem is still unsolved. I don't think this is understood what happens. What are the denominators? So you see, in the case of matrices, because this, from what I said, follows the integers. If you start with the integer entries, your faces were given by integer line forms, then the extreme points are also integers, they're 0 and 1s. But in general, they're rational, of course, but they have denominators. And denominators are, well, complicated. And they depend on kind of combinatorial data of your problem and the size of the matrix, of course. And there is a kind of still, in my view, untouched domain, which was not what developed. And this is one of the questions raised by Vershik, and is still unanswered, okay? So it's number one. And because there will be several different topics, I stayed in 20 minutes, so you may ask questions now, because in 10 minutes before, now I have to run to my lecture on a different subject matter. So if you have a question, you may ask now. So it is a problem. So I repeat it. For example, in dimension 3, you can see the three-dimensional cubical array of numbers, A, I, J, K, and you say that the sum of them over each particular index equals 1, or the array is K by K by K, and you ask, you say you consider all positive such entries when the sum of those by one index equals 1. So what are denominators, what are possible denominators of coordinates of the extremal points, depending on the dimension? At least what is the rate of growth of these denominators, what are their prime numbers, prime divisors of this number, etc. So at least it's not maybe a sharp answer, but roughly what we expect. I think it's quite an interesting question. So you don't have questions, so we'll go to the next topics. And the next topic, this is the most kind of much developed by people are following Vershik, this concept of what I don't know now is called Følner set. And this was suggested by Vershik in my view, getting in the middle 60s, a subject like 65, 66, yeah, for all I remember. And so the point is as follows. It was well known at that time by the work of Efremovich and Alex Schwartz, that groups, kind of essential feature of groups is the growth of this group, which can be understood either combinatorially or more in terms of Riemannian geometry. And in terms of Riemannian geometry, you think about this group as fundamental group of a manifold, say Riemannian manifold, and you take universal covering and see the volume of the growth of the volume of the ball of a given radius. And this could have been expressed in combinatorial terms. It was pointed out by Schwartz, and this concept due to Efremovich. And this was kind of just to notice that by that time there was already this was later. It was probably before Margulis proved the theorem. Basic kind of results showing that it is a non-trivial concept was proven by Margulis. So I'm just debating this remark because people speaking about volume growth usually unaware of that. It was before Milner. Nobody heard of Milner. Actually, I heard of Milner later when I came to the West, but the work of Milner on this respect. There was kind of common knowledge. And what Margulis proven that another systems, so in three-dimensional another system, have exponential growth. So as a fundamental group of the space, of course, I'm saying at that time already nobody would make distinction between the two. After the work of Schwartz, it's of 66 or so. I've forgotten about Schwartz actually wrote the paper. And this is quite a remarkable thing because there are two completely different kind of Anosov system in dimension 3. On one hand, there are geodesic flow on surfaces, and the fundamental group there is pretty big. Yeah? It's a non-amenable group. Or it is or they come from automorphism on the two torus, and when you glue, take a cylinder with such a map and glue two sides. And so the group will be just solvable group. And not nilpotent solvable group. And this is the only example. I don't know by now if it's proven. I think it's known now by now that this is the only example. I guess it is known now. I'm not sure, but the fact is this group grows exponentially, quite remarkable result, and this is still unknown for high dimensions. infinitely far from showing anything of the kind for higher dimensions, because we even don't know its fundamental group is infinite in high dimensions. So it's about growth. But then, and then Vershik came with this kind of idea that there is another growth related to the Følner sets. And so for my shame at that time, I remember he was saying that, and I was perplexed. And I remember I was perplexed what he meant, because kind of I didn't understand the point. And so how we can think about what other characteristics we may have, either space or group or whatever, how we can measure the growth of the volume with what you take. And the first thing, when you take a ball, it's better to say not a ball, but a set of diameter of a given diameter. How big can be the volume of a set if you bound its diameter? And extreme object, of course, or up to a constant list, are always balls, and you know how they grow, and so we can say how big can be a volume of a set with a given diameter. And the maximal volume is a characteristic of infinite space. And now what we can replace diameter with. And you see the whole point that volume measures the volume of a number of points, whatever cardinality is the same entity. But instead of the diameter, you take in something else which behaves linearly in the Euclidean space. And what behaves linearly is the ratio of volume by area of the boundary. Area meaning codimension one volume, right? Now this kind of amusing idea. And of course, there may be other characteristics of a set which have linear growth based on volumes of different structures on it, properly normalized. Normalized, I mean multiplicatively in positive exponents. But this is the simplest coming to one's mind, and this corresponds to what was in Følner set, and this was the idea of Vershik. Now, let me remind you, if you are not well aware of that this everything stems from the work by von Neumann, and as usual, when I mention names, or historically, I have no idea who was the first to introduce this concept. So usually people refer to von Neumann, but I don't think anybody makes serious historical search, and this is certainly a huge work to be sure that von Neumann was the person who introduced concept of amenable group. Of course, he's done that, but was he the first or not? Yeah, it could have been already present in this form or another. For example, as mentioned, the case of the growth of spaces, I refer to Efremovich, was a paper in the 50s, in the early 50s, maybe in late 40s, and still I'm not certain it was not known before, the concept of a growth of a space on the volume. And you'll be not surprised it was somewhere in at least 50 years earlier. And certainly it's not coming up with Milner, who was the last person to refer, and so the last who brought it to everybody's attention. So this may be very annoying. Okay, my time is running out, because I must say I have to run to my lecture, so I finish exactly by 10 minutes before, because otherwise I'll be late in my lecture. Okay, so but that's the concept of amenable group, which for Neumann terms, it's a group such that action of the group in a compact convex space always has a fixed point, if I'm not mistaken. Yeah? Or even if you fixed point, even action in convex and Banach spaces with my minor assumptions. Or another way to put it, any action on a compact space has an invariant measure. So this has been introduced by a phenomenon, and then there is work by Følner, where it was characterized by, in terms of this Følner set, as I say, when the growth of this, how it behaves, and and in more geometric terms, it corresponds to what is called linear, and this is how geometers usually thought about that, linear asymptotic inequality, when the volume of any set is bounded by volume or area of the boundary. But Vershik's kind of radical point was very simple, but we changed this relation between the two, was changed by growth in terms of this linear measure. Instead of diameter, you take this ratio. This looks a little bit stupid, but this happened to be extremely productive, and in particular, it was proven relatively recently, maybe only 30 years ago or something, by that this kind of remarkable inequality but Seleucus with whom I forget, yeah? And that in all groups, the usual volume and this kind of Vershik kind of growth of the volume of the ball, the usual growth of the group, and this growth in the sense of Vershik, they're related by inequality. So if you know a group grows fast, then this second function also grows fast, which means you have strong isoperimetric inequality. And this is quite remarkable. This is quite remarkable theorem, and indicating that this was a very kind of right way to think about this quantity, which was, again, for me, it was very strange first when Vershik was speaking about that, because from the Riemannian geometry perspective, this was very strange way to think about isoperimetric inequality, and that was another idea of Vershik. Briefly about two other things which came up later, if I'm not, I just say it. I'm checking for myself. There are two other observations by Vershik. And one of them, how he suggested, gave new perspective on Urysohn spaces. So Urysohn spaces are kind of injective objects in the category of metric spaces. So everybody can be isometrically embedded into Urysohn space. Moreover, every morphism from a subset extends to the whole set when you go into Urysohn space. So the universal really kind of metric space having maximal kind of internal symmetry. And the fact they exist not a priori not absolutely clear, and they were constructed by Urysohn. And the same concept, we said, don't know who introduced it, whether it was Vershik or somebody else, when it's somewhat more transparent, when you speak about graphs. So I can speak a graph, so any graphs embeds into the graph, and more or less embedding of any subgraph extends to the whole graph when you have this big ambient graph. And their existence was, the construction was suggested by Vershik, just saying, just take random graph. And this kind of beautiful observation. And kind of, because you see that one is kind of categorical type of notion, kind of in its categorical terms, mean this injective object in the category of a certain category. On the other hand, it's also random objects, and this kind of looks paradoxical, and by the way, this object is unique, unique up to isometry. So all random graphs are isomorphic, and of course, it corresponds to usual kind of amazing principle that all random kind of sequences, they're all on one hand different with probability 1, and also indistinguishable. And this is an interesting principle which actually, as Aaron Kohn explained to me, is actually underlies quantum mechanics. This is what quantum mechanics does. Object and quantum mechanics like that. I repeat it without understanding, So, but that's, and in graphs, it is precisely the theorem by Vershik. And this, again, I repeat, is kind of simple, beautiful theorem that all random, infinite random graphs, it's very mild definition of what means random, they're all isomorphic, and they all have this universality property. And it's because, you see, when you construct the proof theorem of Vershik, you use something that there are kind of co-products in the category. And the issue, if this makes sense in all categories, what I mean, random objects in category when there are co-products. And you'll be not surprised that there is such an interesting concept of measure related probably to what is, to Grothendieck topoi or something of the kind. And my last, I have only 1 minute to say it, and this is, as I'm using argument Vershik suggested, to understanding also metrics, random metric spaces, that every random metric space, a random metric space, meaning have a measure and a metric on a measure space. So this you can say is a random metric space, so it's metric on a measure space, or you have to turn it around, you have a already metric space, and say complete metric space, and the measure on the space. And this again up to isomorphism. No, they're not all isomorphic anymore, but they, if say space is a kind of measure is bounded, say probability space, then they're characterized by measures of all finite subsets defined up to isometry. So if you look at all finite configuration of points, they are metric spaces, and they carry measure, product measure coming from product measure of the space. And this character, and what's remarkable, it's proved using only ergodic theorem. If you start naively think about it, you have a little mess and you have to see what happens. But it was a beautiful argument, which I don't have time to say, because besides I don't but remember it, but my time ran out. And so this was the last remark I wanted to make. And it is kind of raises again more general questions, this simple kind of theorem, but and there was some development of this due to Vershik with co-authors more recently of this kind of structures, but I'm pretty certain that it has much general, much more wider amplitude. But when you replace measures by something else, and which makes sense in different categories, but this will be subject of another lecture, but I have to run now. And so I even don't answer a question because I have to go to my lecture.